So now we're going to go ahead and talk about the second part in our overview of threads. If you recall, the first part in our overview of threads had talked about what Java threads are, how they support concurrency, talked about different ways to give code to a thread. I described how to pass parameters to a Java thread. Now we're going to talk about how to run a Java thread. And we're also going to talk about some common thread methods, some of which you've seen before, some of which may be new. And then I think we'll have time for this. We'll talk about the happens before orderings that Java provides via its memory model and which are used by various threading routines and threading methods and threading classes and objects and so on in the Java context. But first, let's talk about running Java threads. So as we'll see more as we get into detail in this, there's multiple layers that are involved in creating and starting a thread. And this is just a sort of a snippet of the stack. And as you can see here, we've got the operating system kernel, which is really where the threads are ultimately going to run. And of course, they're going to run on top of the hardware, the multi-processor cores and so on. There's a set of system libraries. Oh, and the operating system kernel is typically written in C. There's a set of system libraries like libc, which provide interfaces to operating system specific threading libraries like POSIX pthreads, for example. Windows has their own threads, but all this stuff is down below the level that you would ever work as an application developer using Java or Android. Then there's some kind of Java execution environment, such as the Java virtual machine. Different platforms have different ways to do this too, but that's just a common way to refer to it, an execution environment, Java virtual machine being one example. And then on top of that, we have threading and synchronization packages. And that's kind of what we've been talking about at this point, things like the Java thread class. That would be there. And we'll talk more about these layers, and I'll walk through them in a little bit. So when you create a new thread, when you say new my thread or whatever, that actually doesn't do a whole lot. It just allocates an object that's going to be used to do the heavy lifting shortly, but it doesn't really allocate a whole lot. So it just makes an object. In particular, it doesn't allocate a runtime call stack of activation records, which is really the stack that's going to be used to run and keep track of the methods that are called. This runtime stack and other thread resources are only allocated after the start method is called. So when your program, after you create a new thread and you say start, that's where things really start to happen that are interesting. So at that point, a stack will be created, and the Java virtual machine or the execution environment or whatever is running all this stuff will turn around and invoke the run hook method after start creates the resources that are going to be needed to execute the thread. Once this happens, then the thread that's been started and is now able to run can run concurrently with other threads that might be around, including the thread that started that thread. So you can see they can now both run concurrently, and they can block independently. And that's important because if one thread is blocked, but there are other threads that can run, they can keep making progress even if one thread is blocked. Why would a thread potentially be blocked? What would be the thing it would be blocking on? I/O, waiting for stuff to show up from elsewhere. It could be waiting on a semaphore. There's lots of things it could be doing that would cause it to block. But the key point is, as long as there's multiple threads and they're not all blocked, then the thread scheduler and other parts of the system can make sure that they're all making forward progress. OK. Typically, in the run method we have here, any code can be run. And we'll talk more about that, what that means in a second. So in the abstract, any code can be run inside of the run hook method. And that's what it would look like. It would be a piece of code that you would write. And this would either be something that's an interface that you fill in by implementing it, or it would be a subclass of thread that you would go ahead and override and so on. That's where the magic happens inside here. For various reasons, windowing toolkits may restrict which thread can access which GUI component or components. So if you recall, we talked about this with Android. Only the Android user interface thread can access GUI components. So that just kind of shows that that is the only one that can access the GUI components, but other threads could be running in the background doing other kinds of stuff. Now, obviously, if you're building a server-side implementation that uses Java, then these restrictions don't apply in the same way because there's no user interface thread. There's just server threads, and they could pretty much run any kind of code except the GUI code, of course. So that's just pointing out that in theory or in the abstract, run can run anything, but on particular use cases or configurations, you may have to be restricted to certain types of things that can run in a thread. As long as the run hook method doesn't return or hasn't returned, the thread can continue to live and do stuff. So it'll keep running as long as the run method hasn't returned. However, while it's running, the OS scheduler and the underlying execution environment may suspend and resume a thread many times. And that's typical in environments that support some kind of time slicing or time sharing model. If you've taken an operating system class, then you're undoubtedly familiar with this. If you haven't taken an operating system class, in a nutshell, the thread scheduler is the one that's responsible for deciding who runs and who doesn't. And in general, as long as you use synchronization in your code properly, as long as you use synchronized blocks, or you use the wait and notify mechanisms, or you use reentrant locks and condition objects and semaphores, blah, 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 then the fact that your threads are being transparently suspended and resumed over their life cycle should largely be invisible to your program, although the operating system keeps track of it all. The operating system is like Santa Claus, right? It knows what the threads are doing. It knows if they're being bad or good, right? It keeps track of them. If a thread wants to run forever, then you can run its run hook method in an infinite loop. So sort of like a hamster or gerbil on a hamster wheel running forever, going nowhere but running, right? Getting some exercise. You can see here that you could have a run method that does, while true or for ever do some stuff. Now, obviously, in practice, this is only of limited use. You're not going to let it run forever because eventually you'll want to stop it if for no other reason that you're going to have to reboot your device from time to time. But in theory, you could have it run forever. Once run returns, then the thread will die. So when run is done, then the thread is dead. Hey, that's pretty cool, huh? Little rhyme. Threads can either end normally by sort of falling off of the run method. They can fall out of it by returning or breaking or whatnot. Or they can also throw some exception that is not caught, some kind of runtime exception, in which case they will terminate abnormally, but they will still terminate nonetheless. So those are two ways to get them to stop running. There's a method called join that allows one thread to wait for another thread to complete. So you can see here, let's say that this main thread starts off another thread, and they're both doing their thing. And at some point, the main thread might say, I need to have some result, or I want to wait for this thread to exit. I can't make any further progress until this thread is done. So it says, I'd like to join with that thread. And this is an example, a very, very simple example of what we call barrier synchronization. And we'll talk in more detail about barrier synchronization later. So you're basically going to you're going to wait for that thread. Now, keep in mind, if you have a bunch of threads that have been started, you could wait for all of them in a loop. So you could say for, I equals, each of the threads that I've started, I'm going to wait for them all one at a time. That turns out not to be the most efficient way of doing things, but it's a way to do it, and you'll work with that, and it's a common way to do it. There are better ways to do it, but that's one way to do it. Likewise, you can also just have a thread evaporate where you don't wait for it at all. It just disappears. And when that happens, the execution environment, the virtual machine and whatnot, will recycle the resources that are associated with the thread. For example, they will take back the runtime stack and allow that to be reallocated for something else, clean up the memory, thread-specific storage, other resources. Anything that goes along with the thread will be cleaned up by the execution environment so that it's recycled. And of course, that's important because we don't want to have the threads leak memory because you'll eventually run out of memory, and your system will crash because you run out of memory. That's a very annoying problem if you've ever seen that occur on a system before. So that's a quick overview of how you start a thread and kind of what it does during its life cycle as it runs. We'll talk later about more detail about the thread state, but this just gives you a high-level view that's kind of a program-centric view. Let's now talk about some common Java thread methods. So there's a bunch of methods that are commonly used in the Java thread class. Java thread class has lots and lots and lots of methods, not all of which you have to use all the time. So I'll focus on the ones that are most common. One is called a set daemon method. That marks the thread as a daemon. Daemons have certain interesting properties. Daemon threads can be used to run in the background, and the way they work is as long as there's other non-daemon threads that are running, they will keep running. But when all the non-daemon threads exit, the daemon threads will exit too. So it's basically a way of having background threads that will only shut down when all the non-background threads go away so that you can clean the system up easily. We talked about start before. Start's used to allocate the thread's resources, and it initiates the thread execution. When you call start, then the run hook method will be called back automatically by the execution environment, by the Java virtual machine, for example, and that's where you provide your code, the user code. And this is typically called a hook method. A hook method is basically a virtual method or some type of method that's called back when some framework decides that it knows that something's happened, but it doesn't know what to do about it, right? So the thread framework doesn't know what your code will do, but it knows when it needs to invoke your code so that something that you write can happen. That's typically called a hook or a hook method. So start is what you or someone calls to initiate things. So the question was, what is the difference between run and start? So start is basically it's kind of like putting the key in the ignition and turning it over, right? You know, you're starting the car. And then run is what gets called back, which allows things to begin to actually do the user-specified computation, because you override the run hook method. You provide the implementation for that.
Like when we do, like, in our assignment thread.start, is the run just like implied? Because we never actually type thread.run.
Great question. Okay, so the question is, how does run get called back? We'll look at this in more detail later, but in a nutshell, that's the very essence of a hook method, right? A hook method is something that's called back by a framework. In this case, it's the thread framework that's provided to you by the underlying Java platform. And the run method is automatically dispatched after start is called. And we'll look in much more detail later about how this all works. But for right now, start is what gets things set in motion, and then run is the hook method that you have to implement by various programming models we talked about before in order to be able to get the user-specified code to run. So if you don't call start, run isn't going to get called back. You never call run directly. Run is called back by the framework, by the thread framework. Join is used to wait for a thread to finish. We talked about how that's a simple form of barrier synchronization. Sleep is used to have a thread put itself to sleep for a certain amount of time. Sleeps, you have to be a little careful with sleeps. As a general rule of thumb, production code typically doesn't use sleeps. I have sleeps in some of the code that I show you as examples because I want things to pause, for example, for short periods so you can watch the pictures or the lights flash on the GUI. But in general, sleep is something that's not widely used, and it has some serious deficiencies because of the fact that different processors will run at different speeds. So it's mostly for debugging purposes in many cases. Current thread returns to you the thread object for the calling thread. This is a static method, and so what that means is that it'll return for the current thread without you having to specify what that thread is. It can tell it by using the magic of what's called thread-specific storage. Then we've got a bunch of interrupt methods and different variants of them. One of them, which is this one, is used to interrupt a thread, and you'll see later how this works when we talk about managing the Java thread lifecycle in an upcoming lesson. Then there's also ways, so interrupt can be used to interrupt a particular thread, and then we can have various ways to test whether a thread has been interrupted. So the isInterrupted method tests whether a thread has been interrupted, and this method works by being able to be called multiple times without actually changing the interrupted status flag. We'll talk in more detail about what the status flag is later, but for now, think about it as each thread having a flag that's part of its internal state that's specific for the thread. It's unique for each thread. And isInterrupted can be called on a thread object to check to see whether that flag has been set or not. And calling isInterrupted doesn't affect the flag's status. Now, the reason I mention that is because this next method, interrupted, does change the status. And the other thing to note is that interrupted, unlike isInterrupted, interrupted is a static method that works on the current thread. So when you call interrupted, it's a static method, so it says, aha, I'm being called in the context of the current thread. And in addition to being called in the current thread, without you having to specify that thread, you just say thread.interrupted. Interrupted clears the interrupted status flag the first time it's called. So when interrupted returns, that means that the test will check the flag, and if the flag was set, in other words, if the thread has been interrupted, is it interrupted? Well, you'd say it's been interrupted, and it'll also set the flag. So you have to be a little bit careful how you use these two different methods, and we'll talk in much more detail later about how they work. There's also a couple of methods to set and get priorities, which are used by the scheduler to decide the order in which the threads might run. And that's basically the common core set of methods. There are lots of other methods. A lot of the other methods that are parts of the thread class are used for sort of internal debugging and things that the virtual machine or the execution environment will use. But those are some of the key ones you'll use, and we'll use them throughout the course. The last part of this lesson I want to talk about is something called happens before orderings, which is a very mysterious set of things, and I'm going to try to demystify them a little bit. So Java threads methods, the methods in Java threads, can be used or are used to establish happens before orderings. And we'll take a look at what this means in a second. For more information about the happen before relationship and happen before orderings, take a look at this link. It'll give you more detail about that. And you'll see this little example here I'll show throughout this. So happens before orderings are used to ensure that if one event happens before another event, the result of that one event must reflect that happening even if the events are actually executed out of order. And at this point, most people's minds start to melt down because they're like, what the heck would it mean to have happens before? How could it actually execute out of order, and so on? And the reason why things can execute out of order was something we talked about a little earlier, but we'll talk about a lot more as we go along. The underlying compiler, the underlying Java execution environment, the virtual machine, and so on, can actually execute code in a different order in order to make it run faster. But when there happens before relationships that are specified, and we'll see how they get specified, then the execution environment, the virtual machine, has to give a result that appears as if they had executed in order, even if they actually executed out of order for performance reasons. And again, people are like, what the heck does that mean? That's such a weird thing to say. So let's take a look at some examples. So here's a simple example that we see on this slide. So we have two threads, thread A and thread B. And you can see here that this thread A is going to set Y to 1. Then the lock is going to get set, and it's going to set X to 1. And it's going to unlock the lock. And the key thing to note is that everything before the unlock on M, all the changes that occurred, especially to x1, x equal 1, that change that occurred here will be propagated throughout the caches on the multiprocessor or multi-core environment, such that when this code runs, it will see the latest version of X. So when this code runs, if this lock is acquired, and then this lock will not be acquired, because if you come along to get that lock, this thread will have to wait. After unlock is called, then the value of X will have been flushed out to every thread in every thread cache in the multiprocessor or multi-core environment, so that when this lock is acquired, X will have the appropriate value, and it won't have some half value, or so on. So that's an example of a happens before relationship. This has to be flushed out to everything before this code can actually run. Now, so anyway, that's the key thing that's being said in that case. And we'll take a look at some other examples here in a second. In general, a happens before relationship guarantees that memory written to by one statement is visible to another statement. So here again, we can see that we have an answer, and we set the flag ready to true, and we want to make sure that this statement, if you have the happens before relationship put into place, that this statement will complete its write to ready before this statement reads the value of ready. So that's the happens before relationship. Now, as we'll see in a second, if you don't use the synchronizers and you don't follow the Java memory model, then the compiler and the virtual machine and the execution environment, et cetera, are free to reorganize things in all kinds of crazy ways. And so you may actually end up with things passing each other in memory. Yes,
So,
Jesse?
I don't understand because it says in the happens before definition that the result, even if they're executed out of order, aren't those, like in thread 1 and thread 2, aren't those things being executed in order?
If you don't use the proper synchronization, then as we had talked about in other contexts, it could turn out that this value answer does not get propagated properly to this thread. If you don't use, the key point to remember is ignore what appears to be temporal relationships between the way that these two things are laid out on the screen. If you don't use synchronizers properly, then this flag might be set to true, but answer may not be 42. So that's the key thing that's important to remember about memory models. If you don't use synchronizers properly, then stuff can appear in different orders. It can execute out of order, and not everything that you read and write to in a linear, sequential way will be flushed out to the caches of the other threads in that order. And I'll show you some examples in a second. Yes?
Wait, so is it possible if you don't use synchronizers properly to ensure that, to like establish this happens before the relationship and make sure it executes correctly?
So the question is, if you don't use the synchronizers properly, if you run afoul of the memory model, what will happen? And it turns out that if you don't use synchronizers or the memory model rules properly, then you could get sort of crazy from your point of view. The system is just optimizing things because you didn't tell it not to. So it can rearrange the orders of reads and writes in memory. Reads and writes can pass each other in memory. So it might turn out that maybe ready gets set to true, so this flag will be set to true, but answer will have an old value, even though answer was set to 42 before ready was set to true. If you don't use synchronizers properly, then there's no reason that the answer in thread 2 will actually have the value that was set ahead of the ready in thread 1. And that's the wacky part. So the key thing to remember is if you want the order to matter, you've got to use your synchronizers properly. And if you don't care, then you don't care, but you're not going to have this ordering properly. So let's take a look at some examples. This might help make it a little bit more clear. So underlying all this stuff is something that's called the Java memory model. And you can take a look at this link, and it'll give you an overview of the memory model. You can download the spec. If you're having a hard time falling asleep at night, then read the spec. It's really dry and boring, but it describes all the rules that the implementers of a Java virtual machine and execution environment have to follow in order to implement these rules properly. So here are some examples of memory of happens before relationships in Java. So if you start a thread, and this goes back to Duncan's question from a few minutes ago, if you start a thread, say start, then the thread initialization, all the things you got to do to get that thread up and running, happens before the run hook method of the thread is called, which makes sense, right? If you were to say start on the thread, and then before the start had finished initializing properly, the run method was called, chaos and insanity would break out because you'd be trying to access the thread resources by the run method, but it hadn't been fully initialized. So here's an example. So here we have thread T1 equal new thread, and I'm going to give it a lambda expression. We'll look at that in a second. And we call start. So this lambda is going to play the role of the run hook method. So I'm going to call start here, and this hook method, which is the anonymous lambda expression that's playing the role of run, this will not get called before the thread is up and running. Its internal state is all initialized and consistent. And of course, that's exactly what you want, right? You would hate to have the case where this code inside the lambda expression would run before the thread was finished being initialized. So that's an example of a happens before relationship. The Java execution environment will ensure takes place before it lets this thing actually start to run. There's also lots of examples of happens before orderings in the Java util concurrent package classes. So take a look here. Here's an example where we've got thread 1 and thread 2. And thread 1 is going to put a value into a particular key in the concurrent map. And thread 2 is going to get the current value at that key in the map. And what happens to happen here, because otherwise, again, chaos and insanity would occur, is that this value has got to be stored in the map and finished being stored consistently, and then be properly flushed out to any other threads, like thread T2, before you'll get back a sensible value by calling get. So in other words, the put has to happen before and has to have completed before you can go ahead and get the result. And if the happens before relationship didn't occur, then you could have the key in the map, but the value wouldn't be there yet. And then when you went to look up the key, you'd get back some sort of random garbage, which would be bad, right? So that's another example. Now, for both of these situations, for the threads that we looked at here, starting a thread and we're having run called back, putting and getting elements into a map, the way this works is if you were to look at the code, you would see that there were synchronizers inserted, things like, atomic test and set and this kind of stuff, or compare and swap. They're things that the implementation is doing to make sure this all works properly. And they typically work by having synchronizers in place to make sure that not only is the code not full of race conditions, but that the memory is properly pushed out to the caches. Here's another example. So terminating a thread happens before a join with the terminated thread. So here we go ahead and we're doing our hello world print output from this thread T1. And this thread will terminate after its lambda expression completes, because it's a very short example. And this thread here, this whatever thread created thread T1, the join will not return until this thread has finished running. So once again, just making sure that this happens before, right? This thread will complete before join will return. So those are some of the examples of the way that this works for some of the thread stuff.